So one strange application of integration is actually finding volumes. Okay, and I say that's strange because when you take an integral, you're computing the area. So we spent a long time studying areas, and it's sort of strange talking about volumes. Now, I'll admit that the main ways to compute volume will be learned in later calculus classes, in Calc 3 in particular, where you'll integrate functions of two variables. Okay, and that's sort of the most appropriate place to discuss volumes. But here we'll take a look at some preliminary ways to compute volumes for very simple shapes. Okay, so for very simple shapes we can compute volumes using basically one-dimensional integrals. So first we'll discuss how to compute volumes using the slicing method, and here's the general slicing method. Okay, here's the big idea. You generally have a cross-sectional area at the point x that's easy to figure out. Usually this is, you could get a formula for it. Usually it's a circle or a rectangular, something where the cross-sectional area is really easy to compute. And if you multiply that by the thickness dx of that slice, you get a volume. Okay, this is an area times dx, and so you'll get a volume, and you add those small volumes together. Now, sometimes you want to take slices not along the x-axis but along the y-axis, and so you'll get a formula for y instead, where you take a slice that's perpendicular to the y-axis. Okay. The best way is to take a look at a concrete example, and we'll see how you can compute volumes using integrals, or just integrals of one variable. So here we have a solid with a base that's bounded by the curves y equals x squared and y equals 2 minus x squared. And so you could see here's y minus 2x, y is equal to 2 minus x squared, and here's y is equal to x squared. The cross sections through the solid perpendicular to the base and parallel to the y-axis are semicircular. Okay, so that's key over here. We want to find the volume of the solid. So here's what's going on. You basically have a semicircle with radius of what I'm highlighting right there. Okay, it's bounded by these two curves. So over here you could get a basic view of what's going on, what we're trying to compute. What you'll see here is the base, so you can see that this is bounded by the two curves y equals x squared and y is equal to 2 minus x squared. And here's how a slice looks. Okay, and you could see that how big the slice is, the area of that slice depends on x. Okay, so if we go a little bit farther down, we'll get a smaller one, and we go farther down, we get yet a smaller one. And so that's our a of x. That's the area at a particular x. Okay, and what we'll do is take that area and multiply it by a small thickness dx, and add all of those together to get the volume of a solid that you see over there. So that's what we're doing, and each one of these is a semicircle. Okay, each slice is basically a semicircle where the diameter is bounded by the two curves. So continuing now with the problem that we have, okay, we'll see that the diameter is basically you just subtract the value at a particular x of the top function minus the bottom function there, and so that's what we have here. And so you'll get that for a diameter. Well, the radius is going to be 1/2 that diameter, and the area, and again this is a semicircle, so it's the area of a circle with radius r is pi r squared, and we're going to divide that by 2 to get the area of the semicircle. And so here's our a of x. Okay, and now we want to know from where to where we integrate, so we set the two curves equal to each other, and we see that they intersect at x equals -1 over there and x equals 1 over here. And so we're going to take our cross-sectional area AX, multiply it by small thickness dx, and here's a volume, okay? And now we're going to add all those small volumes from -1 to 1, okay? And we just do a straightforward integral now in one variable, and we get 8 pi over 15 as our final answer.